always add 20 minutes to the schedule, please. So much for some housekeeping. I'm very happy to be able to announce our first speaker for today. It's Stepan Snigirev from Spectre. He's the CTO of Spectre Solutions and has been working on Bitcoin software and hardware wallet for 3 years now. So please welcome Stepan.
I need to find my presentation, I suppose. Okay, while this is all going on, let me maybe start, and because the first slide is anyways just the title, right? So no one cares about the first slide. Yeah, so what I want to talk about is Taproot on hardware wallets. So we recently got a Taproot upgrade, yay! Yay! This is awesome, so like activated in November. Yeah. This is the slide, actually. Good. And even some of the software wallets started integrating that, and even some of the hardware wallets started integrating it. But they're using like a really tiny fraction of the capabilities of the Taproot, because right now, what everyone is using is just a boring single signature, single key approach, right? So I want to talk a bit about what can be done with the Taproot. I think everyone knows, so I will be pretty fast here. And then I will discuss why it is extremely difficult to implement on the hardware wallet, and what exactly is difficult on the hardware wallet. And if we don't get it on the hardware wallet, where we can get it. Okay, so Taproot is awesome. First, it gives us the privacy. Because when you see something on the blockchain that looks like a single signature and the single public key, what can be inside is a key and a tree of scripts. And the key itself can be a collection of keys, and this script tree can be also a very deep and complex collection of scripts. And here you can have any kind of time locks, backup keys, whatnot, that are normally not used, and you use them only in case of emergency. So this means that all complex policies will look the same on the blockchain, and this is huge. And even each of these keys that are inside any of the structure can be also a collection of the keys. So it's like infinite power of the key aggregation. So this is really cool. And first thing that I would personally use this for is actually better plain text backups. So the thing is, why nobody uses miniscript right now, or complex Bitcoin scripts? First, because Bitcoin scripts were too complex to write before miniscript was introduced. And second, because everyone is not using it. So we kind of have a chicken-egg problem where everyone is using either single sig, that is like 90%, multisig 10%, and only 0.3% is using anything custom. And so if you are using some custom scripts, then you basically expose yourself in this 0.3%. So all chain analysis companies know that if this script is used, this is probably the same guy. So this is really bad for privacy, and this is one of the barriers. The second one is about the implementation of the miniscript. So what you basically have, for example, what I would use personally. I'm extremely scared of plain text recovery phrases that are lying somewhere in my house, and if someone breaks into that, I basically will lose all my funds. So what I would personally use, I would use a hardware wallet that I don't back up. And I have the backup script where I use a time lock plus the recovery phrase. And then if I screw up and my hardware wallet is broken, I need to wait for maybe half a year, but then I get my funds back. But if my recovery phrase is compromised, then they will not be able to send to steal my funds while I have the hardware wallet. So I have enough time to basically migrate to a new setup. And if you are thinking about the hardware wallets and miniscript implementation, none of them is really supporting it yet. Yep, too bad. But it is not actually very difficult. So when I was integrating miniscript in our hardware wallet, it basically took me just 1 week. I just sat and wrote the freaking thing because it is extremely good, well documented. So there are two components. One of them you can just ignore. So one of them is when you have a policy that is human readable that you convert to the descriptor. It is kind of complex, but you don't need to do it on the hardware wallet. And then the second part is when you compile the descriptor to actual Bitcoin script. And this is pretty much just a replacement of these operators to the op operators in the Bitcoin script and placing the derived keys in the right spot. So it is pretty easy, and then the hardware wallet will be able to determine which output is the change. So it can verify that the change output is derived from the same descriptor, and then you're good. So I want to mention that actually Ledger recently did a lot of work in upgrading their Bitcoin application, and they took this miniscript approach while designing it. So even though right now it only supports Multisig, it's actually pretty easy to upgrade it to support custom miniscript. So looking forward for that. Regarding other hardware wallets, I don't know about their plans. But at least then there will be 2 hardware wallets that support that. OK, so this is, I think, very useful. And another use case is, let's say you are running a collaborative custody company. And you want to give the users the ability to store one of the keys, like to use one of your key in their multisig setup. For example, they have a 2 of 3 multisig where 2 keys controlled by them and 1 key controlled by the company. But you don't want to rely on a single point of failure for your key. So you want to give the user 1 key, but you don't want to have actually 1 key. So what you can do, you can actually split it into, well, basically have an interactive multisig. And here, you just need to combine them in such a way that you can give the user a single XPub. And it is actually possible because how BIP32 and XPub derivation works, it just tweaks your public key with a certain hash-based scalar. So it is doable if you combine the keys in advance. So like when you're constructing this XPub, you take the chain codes, you add them or XOR them, you combine the public keys with a normal music setting or whatever you use. And then when you need to derive a new child key, you just use this aggregated chain code and public key to derive the next keys. And you will be able to sign it interactively between your devices. So these are awesome applications. But they are relying on this interactive multisig that I said a few times. And if you look at the papers, how many approaches there are to kind of build an interactive multisig, there are at least 5. At least these are 5 that I know of. And this means that each of them introduces a certain trade-off. And if you have a certain trade-off, this means that you actually have a trade-off. So there are like security problems in each of them. And I want to talk a bit about all of them and why they're hard. So these 3 on the left side, yeah, right. So I should probably remind you the Schnorr signature, right? So basically, if you want to sign, you pick a random nonce. You hash this nonce together with the public key and the message, the public point of the nonce, and then multiply it by your private key and add this random nonce that basically hides your private key in the signature such that, well, no one ideally should never find out and calculate your private key. And then the verifier can just take your signature, multiply it by the generator point, and verify that the equation still holds. So if you are trying to do it in the multi-signature setting, you basically have the same with a few problems. First, here we have the nonce in the hash. And each of the cosigners need to generate their own nonces. So the first requirement is that they all should communicate to each other and say what nonce they are using. And only after that, when you kind of aggregated the nonce, they can generate their shares of the signature. And then they can just, the software wallet, for example, can just add them together, and you get the final signature. So the scheme is also not super complicated. You just need to have additional round where you coordinate the nonce. And then why there are so many papers. So the first one is Multisig, that was probably the first one that was introduced, and it relies on the key aggregation in n of n setting. So you have either 2 of 2, 3 of 3, 5 of 5. So you cannot do 2 of 3 or 3 of 5. And it requires 3 rounds. So the first round is when you pick the nonce, you hash it and send to everyone else. Then when you received all the, this is basically a commitment to the nonce. This means that you say that, okay, this is the hash of the nonce, so I commit to it, I will use this exact nonce. I cannot change the nonce anymore. Then you send the nonce itself, and you get all the nonces from other consigners, and you verify that they used what they committed to. And only after that, you generate your own signature and aggregate the signatures. So 3 rounds is terrible, especially if you are using, like, let's say you have multiple hardware wallets distributed across different geographical locations. Then you need to run around 3 times across all of them. And while doing that, they also need to maintain the state here. So they still need to remember about all the commitments and stuff like that. And this is not how current hardware wallets work. They try to be stateless. They try to be not really interactive. So then there was a Multisig 2. This is an upgrade of Multisig, where you remove this first round of commitment, but instead of that, you generate not a single nonce, but you generate 2 nonces. And then you share this nonce with everyone else. You combine it with some hash-based coefficient. I don't want to go into details, but this way it is secure under certain assumptions. If you want to make it even more secure, you generate 4 nonces. So this relates to some cryptographic funky things like forking and time machines and whatnot. So I recommend you reading the paper if you want to get into details. But basically, yeah, just generating 1 extra nonce makes everything secure, and then you have 2 rounds. And 2 rounds is already much better, because what you can do, you can generate the nonces in advance. You can gather 100 nonces from each of the hardware wallets, and then you just use them when you need to sign. And then you actually need to run through all your hardware wallets only once. But this, again, requires the state, because the hardware wallet needs to know about the nonces that it generated, and it needs to verify that it didn't reuse the same nonce twice. Because if you reuse the same nonce, then you're screwed, because you basically lose your private key. Okay, and then finally the Frost. Frost is interesting because it is not focusing on this nonce negotiation. It is focusing more on the key aggregation. So it allows you to do 2 of 3, 3 of 5, something like that. And the idea there is you use a verifiable Shamir secret sharing scheme. So basically, the idea is that if you want to do 2 of 3, if you have 3 private keys that are on the same line, then you can derive the this kind of combined private key or public key or the signature, only having 2 of them. So any 2 points of these 3 can help you to reconstruct the final signature. So this means that the only problem is how to make sure that the private keys that we generated at random will end up on this line. So the main idea of this Frost's paper is how to communicate between different hardware wallets, or not hardware, different signers, in such a way that they end up in the same line. So it is an interactive scheme, but it is very nice because after first interactive setup, you can move them around and you still have 2 rounds. But again, all these 3 schemes are relying on the fact that your nonce is never reused. So this means that in order to generate fresh nonces, you need either a counter or a random number generator. And these are 2 problems, especially on the hardware wallets, because I can hack the counter, I can hack the random number generator. And let me show how you do this. Okay, so first idea is just use the counter. So you just have a number that you always increase and never reset, never reuse the same value, and you hash it together with your private key to get this nonce. Yeah, and then when you use something, you increase the counter again. So it works perfectly in theory. In practice, there are plenty of attacks. For example, what Fraunhofer Institute did with the unlocking STM something microcontroller, they just shoot the laser into the thing. So if you shoot the laser into the right spot of the flash memory of the microcontroller, it will reset. Either it will go to 0, or you will flip the bit and it can go down in the counter, so it can be reusing the same counter again. And here, the problem is that as this is the nonce in the signature, this means that it will be on the blockchain. So, or it is known also for your cosigners and your software wallet. And this means that if there is not enough entropy or it is reused, then they can recalculate your private key from the signature. With a random number generator, there is a very nice talk at DEF CON where they talk about problems of random number generators for 45 minutes. So I think this means that even if you are using a very certified closed source random number generator, it's normally not enough. And most of the talk here actually is about how you can screw up the random number generator yourself as a developer. And it doesn't even touch the problem of the hacking that random number generator. Okay, so how you can screw up with the random number generator? First, it happened in the wild. Sony PlayStation 2 was hacked this way because they reused the same nonce and basically leaked the private keys, so you could homebrew your PlayStation 2 with this leaked Sony's private keys. YubiKey, when they went through the certification process, they got certified, but they screwed up with initialization of the random number generator. And you only had to have 3 signatures to reconstruct the private key, so there was a huge problem there. Then, as I mentioned on this talk, they analyzed output of true random number generators from the different microcontrollers, and what they saw that sometimes you accidentally get a bunch of zeros, so your nonce is 0, that is bad. Then sometimes it repeats the same value multiple times because you're asking for random numbers too often, so it just wasn't able to generate a new random number. And also, sometimes TRNG fails because there is a voltage glitch, or just for some mysterious reason the proton from the sun hit the microcontroller and something happened. By the way, this can also happen with the counter, so you will be very, very unfortunate if this happens with your hardware wallet that uses the counter. Yeah, so basically this is how you can shoot yourself in the foot. Now let's say someone else wants to shoot you in the foot. How you can do this? Let's say we have, this is the most common probably true random number generator architecture, a ring oscillator. Basically because it is using standard NOT gates that can be easily done in the semiconductor. So basically you have a NOT gate that converts 0 to 1, 1 to 0. Then you chain 3 of them one after another, such that you get some time delay, and then you feed the output of the third one to the input of the first one. So this becomes this ridiculous logic circuit that is constantly switching between 0 and 1, and the timing between the switching is very dependent on the environment, on the manufacturing imperfections, on the impurities of the semiconductor, so on all this stuff. This basically gives you a very unpredictable output. And to get even more random numbers, you basically take a bunch of these oscillators and XOR them together. Okay, looks good. So now I'm asking you to remember your physics class, like high school or, I don't know, elementary school, whatever. So what happens if you have multiple pendulums on a rod? On the rod, everything is fine. They are oscillating with their own frequencies. But what if you put it on a rope that actually can transfer energy from one pendulum to another one? Then, after some time, it will synchronize. And you will Google it on YouTube and actually see how it works in action. So the problem is that if you have a bunch of oscillators that are coupled together, they will eventually synchronize, and then your random output will be not random anymore. And even though, like in the certified, good, well-designed random number generator, there are some countermeasures, and they check that the output is fine. But what happens if you just put your microcontroller on the PCB board that is poorly designed, that has a trace going through all of them? It can introduce this coupling. Or if there is an attacker, like evil-made attack, that just takes your device, disassembles it, and puts some wire there, it also can introduce the coupling. And then you're screwed. Another types of random number generators are also not perfect. If you're using like something that is dependent on the temperature, you can freeze these things. Then also you can just lower the supply voltage of the random number generator, and it will output zeros more often than once, or just do some weird stuff. And weird stuff is where low entropy is, right? So you don't have enough entropy, your nonce is brute forceable, and then you're done. And also all kinds of fault injections where I can just take an electromagnetic emitter and also force all these oscillators or the random number generator to malfunction. So random number generator is bad. Well, it's not perfect. So is there a solution? You saw that there are 5 papers, right? So on the second column, there are 2 papers that don't require random number generator. Yay, right? So they use deterministic nonces. And they use not just deterministic nonces. They use a verifiable deterministic nonces. This means that your hardware wallet or your signer can generate the nonce and prove to everyone else that it was generated deterministically using a particular algorithm. So yeah, Multisig DN is Multisig deterministic nonces. And 21 is something from Facebook. Yeah, so they actually published this paper, but it is a very nice one. Looks like a very good solution, right? The only problem is that generating of these proofs that you generated the nonce deterministically is pretty complex. So for example, in Multisig DN, the benchmark says that if you are running it on an Intel Core i7 3 GHz, so like a normal computer, it will take 1 second to generate the proof. So now if we think about hardware wallets that are 100 megahertz maybe, and they're also 32-bit, not 64-bit, so you can easily get a factor of 100. And so here is the comparison. The first 3 guys are relying on RNG, so we don't care about the benchmarks, it is fast. But the last 2 guys, this one, on the microcontroller it will probably take 100 seconds. So if you have a 5-input transaction, you will need to wait for 10 minutes. So not great, right? Also, the memory requirements are pretty high. I think that it can be optimized, but still, 10 megabytes is not what you have on the microcontroller. There you normally have like 100 kilobytes, something along this line, maybe megabytes you can get on the high-end ones. Well, yeah, Keystone, for example, that is Android-based, can have plenty of memory, but actually they are running the secure code on the secure element that is also not very performant. So, and the proof size is, well, okay, 1 kilobyte. I'm a QR code guy, so I don't quite like transferring 1 kilobyte over QR codes. That will be complicated, but okay, fine. And then finally, the second paper, it uses a different zero-knowledge proof. So it is much faster, and on the microcontroller it can actually run. On the memory, I'm not sure, but I think that it is also using a few megabytes. And the proof size is 1 megabyte. So it's like the whole freaking block of Bitcoin blockchain is just a proof that you generated the nonce properly. But you don't need to broadcast it, right? So it just internally transferred from one signer to another. Yeah, so this is the summary of all multi-signature schemes. All of them, as you see, have certain trade-offs. And I would say that if you are using multiple hardware wallets that you don't want to connect at the same time to the same computer, and you, for example, have them distributed, then don't use interactive multisig. Use just a normal multisig. Unless until we get some reasonable music implementation. But there are plenty of use cases where it is extremely useful. For example, Lightning, completely different security model. Your keys are always online anyways. You need to keep the state anyways. So it just doesn't increase your attack surface if you start using music. So Lightning, good. Then atomic swaps. Also, probably you're using it in a single sig setup. And yeah, so here you need actually to have multisig. Yeah, basically here also you have it probably on the hot wallet, so very similar situation, also keep a state, so also fine. Then for services where you have a server that is signing like one of the signers. So like Blockstream Green uses 2 of 2 or 1 of 2 plus time lock. So this can be really optimized for Taproot. Moon Wallet is using 2 of 2. The guys at Square are doing something funny with the server, mobile wallet, and kind of secure key storage thingy. So these are very good use cases. And finally, my favorite, my dream, my passion, my precious. Yeah, I'm dreaming about that already for like 3 years, but never had time to implement, is a paranoid HSM, where you combine multiple chips in the same device. You take a RISC-V FPGA board that is fully open source. You take a secure under NDA secure element from Infineon, for example, or an XP. And you take some other ARM-based microcontroller, for example. And each of them had a key. And each of them share like needs to sign in order to generate the full signature. And then if the attacker wants to hack this thing, he needs to hack 3 different microcontrollers. This is really, really great, especially for like HSM enterprise use cases, because, well, in case of HSM and enterprise, you can also cover it in the Faraday cage and also have a mesh of conductive mesh that detects all the tamper attempts and so on. So this is like really, really, really cool, but yeah. Yeah, so I think Taproot is awesome. I actually have like 4 minutes for questions if you have any. And we should, yeah, let's see how it evolves. I think it's really nice. Any questions?
On what Lightning wallets can I use Taproot multi-signature today?
So I think that right now it is not even specified in the specs, so I don't think that it is implemented in software yet. I think that C-Lightning is actually working in that direction, but yeah, maybe better to ask that Chris Decker, that should be here somewhere. Yeah, here, hi. But I think that it is still in the let's write specification step. But in general, basically, this would mean that all your channel opening and mutual channel close transactions appear on the blockchain as a single signature and single key. And only if you need to do unilateral close, then you will expose the fact that there is a time lock in the top tree.
Which one of the collaborative multisig schemes do you think are on the path to mainstream adoption? Because we have like weird situation when you have 14 standards, then we need to create one standard to rule them all, and we have 15 standards.
I don't know which one will be the one that is used by everyone. I personally like music probably, and some kind of maybe combination with Frost, because it gives you the threshold signatures, because it is like 2 of 3, something like that. But from my understanding, the Frost will have problems with the cross-input integration. Sanket mentioned that. And so I don't know. Frankly speaking, I don't know. I think that it makes sense to start looking at music first, because this will be probably the first adapted. But might be better to ask someone who is writing libsecp 256K1. Yeah, I don't have a definite answer right now.
Hi. So, are there any hardware wallets that sort of allow you to provide your own entropy for the random, for the nonce, basically? And if not, is there a good reason why not?
I know that, basically, before all the Taproot stuff, what was discussed in the kind of hardware wallet and Bitcoin community was the verification and kind of mitigations of the chosen nonce attacks, nonce nonce side channel thingy, where the hardware wallet, when it is hacked, can leak your private key. So I know that 2 hardware wallets implemented mixing of additional entropy into their signatures. This is Jade and Bitbox. As far as I know, no one else implemented that, but this is pretty much the first step for music. So I think that basically we can reuse the same specs and protocol for music coordination as well. And I think as soon as other hardware wallets start, if they will start implementing music, they will need to have this API for mixing additional entropy.
Hi, you mentioned RISC-V. Do you think there's any scope there for custom instructions to try and make this, really quick, or because it doesn't seem like there's a lot of basically you have to emulate everything, right? Use software implementation for everything.
Okay, so with the RISC-V on FPGA or just general RISC-V? Because
yeah, FPGA.
FPGA. So I would recommend to look at Precursor, the project from Bunny, the communication device, secure communication device for journalists and stuff that it was on crowdfunding and was crowdfunded, and now they're manufacturing it. So the guys are really into hardware. They use FPGA and the RISC-V core on the FPGA. So I think it makes sense to look into that. They also have OS and stuff. And some secure measures, actually. So in principle, they are also fully open source. So what we can do, we can take everything that they did and use for our benefit. But I think that open source RISC-V cores are evolving fairly quickly and getting more production ready. Yeah, and in this setup, for example, you kind of don't need to hit really the production ready state because you also have additional security by other chips. Yeah. I think that there are also a few FPGAs manufactured in China. I don't know how much you trust China, and that actually are extremely cheap and that can run RISC-V in the minimal implementation. But generally with FPGAs, if you want RISC-V and reasonable speed, you need to pay premium because FPGAs are more expensive, or maybe a few hundreds dollars. Yeah.
Thank you, Stepan.
Thanks, guys.